Okay, so now the next part is we want to find the time involved state and the norm of the time involved state squared. So the first thing you'll find is because our Hamiltonian is constant from time, we're able to apply a evolution operator. So essentially what we find is if h of t is equal to h, then the evolution operator is just e to the minus I e t over h bar. Now, when you go and take further quantum classes, you're going to have to use a time-dependent operator. But for now, in the infinite square well, we find that it's constant, so we can use this operator. So the first thing we do is we use equation 2.16. There we write our psi of x of t as the sum from 1 to infinity Cn times psi n of x e to the minus I e n t over h bar. And here we've used the fact that psi of x and t is equal to psi of x times e to the minus I e t over h bar. This is equation 2.7 in your book. So the goal now would be to apply the evolution operator on this state. But what we find is that because we're only using the number 1 and number 2 state, we have n going from 1 to 2. So that actually simplifies our expression a lot, and it allows us to solve this analytically. So what we'll find is psi of x and t is equal to 1 over the square root of 2 times psi 1 of x e1 of t psi 2 of x e minus I2 of t. Now what happens is that we can keep writing the rest of these terms like psi 3 plus psi 4, etc. But the probabilities associated with each of those terms is just 0. So then each of these terms are just going to be identically 0 because they have 0 probability. So we set them equal to 0, which just leaves us with the basic solution for psi 1 and psi 2. So now that we've found psi of x of t, we're going to try and find the norm, and we're going to do that by just squaring it by its conjugate and itself. So we've done this before. Psi of x of t is equal to psi times psi star. I've left out the x and t dependence here, but you can put that in yourself. So what that equals to is 1 over root 2 times psi 1 of x e to the minus I e1. And we're going to multiply that by the conjugate. Now notice that when we multiply this out, the terms with the same number are going to have canceling exponentials, and the terms with different numbers are going to have exponentials that don't cancel out. So when we have this term here, we're going to see that these two terms cancel out, so that just goes to 1. These two terms cancel out, so that just goes to 1. So we get psi 1 x squared plus psi 2 x squared, and the cross terms with exponentials that don't cancel out to 1. So I'm just going to cross this part out. So using these values, we're going to also use equation 2.31. And you're going to find that psi1 of x is equal to and again, we can just square these norms to get the norms of them. Now, what we're going to do is we're going to take these values and plug them into our big equation for psi of x and t squared, and also accumulate these psi1 and psi2 terms that we've found using our equations. So what we're going to find is that psi1 of x times psi2 star of x is equal to square root 2 over a and we can do the same thing for the other one. So using these terms that we've found and this equation we see below, we can get our equation, we can simplify our equation more for psi of x and t squared. So this term is psi1 squared, and this one is psi2 squared. Then we're going to get the cross terms. So and we're going to add in the exponentials that we had that didn't cancel out for the cross terms. And we're going to do this for the other cross term as well. Now what we're going to do is we're going to collect these terms together because these two are obviously the same thing. And we're also going to use Euler's formula to write that in terms of sine and cos. So I think because there's a minus sign here and we have no imaginary numbers, it's going to be cos. And then we're going to have the combination of e's. So that's going to be times e to the minus I. Now notice that if we set this phi to be e1 minus e2 times over h bar, then we can, once we do that, we can write out the linear combinations of e's in terms of cos. So here we've just got the half from our normalization factor, and they cancel out with all the other terms, and we can factor out to get 1 over a. So here, after this, notice that from equation 2.30 in your textbook, you have the value of en, which is equal to n squared pi squared h bar squared over 2ma squared. Notice that this section here is actually just omega. So then we can write that equal to n squared omega h bar. And therefore, when we set our n's to be 1 and 2 for the two states we have, we find that E1 is actually equal to omega h bar, and E2 is equal to 4 omega h bar. Now notice that here I can flip E2 minus E1 and get minus E1. I can get minus E2 minus E1. These are the same thing. And this minus can come outside the cos because cos minus x is equal to cos x. So therefore, we don't really need to worry about writing it as e1 minus e2 here. So once we write this out, what we find is our final value for psi of x and t. So just a bit of physical interpretation to this. The first element corresponds to the first psi1 wave function, and the second element corresponds to the psi2 wave function, which is standard in time, and then this element corresponds to the mixture of the two elements. And that's sort of like your entanglement term.